Thank you, everybody, for being here. Can everybody hear what I'm saying? Yes? Okay, so today I'm going to briefly introduce myself. My name is Gabriele Vaccari. I work for GoLab, which is a Japanese company which does collaboration software. And I'm going to talk about how to build an event-driven system in Go. So this is going to be a tale, basically, about our experience in doing this. So what I'm going to do is I'm going to talk a little bit about our system architecture so that you can understand what the context is. And then I'm going to talk about some of the design choices that we made that we thought were good design choices. And I'm going to give you some development tips in case you're interested in developing your own integration with RabbitMQ. So it's like you will see that it's easy to find and use some of the open source libraries that are available on GitHub to connect it to RabbitMQ, but some of them come with an additional complexity, which is basically given by the protocol itself, AMQP. So I'm going to give you some tips and that you might want to remember so as to make like better informed choices when you develop your own code. So the first thing that I want to talk about is our system architecture. So basically, it all began when we decided to migrate from a monolith, a big, bad Java monolith, to a microservices architecture. So that happened a couple years ago. So we had this very big server containing our Java application, which has basically all the backend for our product, which is this one I'm going to talk about. And it was very hard to maintain. So at some point, we decided to come up with something better. And we split everything in microservices. And we took the opportunity to do that in Go. And I know that also our colleague here from Red Hat talked about gRPC yesterday, right? So we did that with gRPC as well. And that enabled some interesting patterns for our system. So this is what it looks like, basically. And actually, this is a very simple representation of our current architecture, but it just gives you the idea. So at first, we had this big Java monolith, right? And then we split into around 7, I think, microservices. So all of these are small components that provide the APIs and all the basic business logic that we use in our software. It runs inside a Kubernetes cluster, and it leverages Envoy as the HTTP2 load balancer, and we use Postgres as our database. So at some point, we found out that we wanted to have something more in our architecture. So we wanted to have, like, for example, a notification system, which is the one that you see like in Facebook when you log in and you see the small bell icon with the number right to it. And we wanted to have like email processing. We wanted to have some stuff. So we thought how we could go about it. And since we already had this microservices architecture, which was very flexible, we wanted to use basically the same approach and to try to do something that was equally scalable. Oops. That was equally scalable and easy to deploy and to maintain. So from this, basically, so yeah, these are some of our goals of in terms of features as well in terms of system of our system. As I mentioned, the in-app notification system and email processing. Then we have also webhooks. Like some of the objects inside our product can be connected to external systems. Like, for example, Slack. That is the Slack icon. So, so when you do something, you can automatically have messages in Slack. And then we wanted to have UI real-time updates. And we wanted to do that with WebSockets specifically. And then we wanted to be able to extend this at will. So, for example, in the future, we might have like a tracking system to track what users are doing with our system. We might want to have like more or different webhooks, more stuff. So the goals are pretty simple. It has to be scalable, easy to maintain, and easy to extend. So what we came up with is like this was the intermediate step, which basically features a broker. In this case, this is RabbitMQ, and some other small services written in Go, which build up the event system. And there is also an EventDB that you see there, which is something that we use basically to store processed events waiting for the actual API providing microservices to read and to provide it to the front end. And as a second step, we added also a UI event processor with a separate broker to handle this. So this is how it looks like more or less today. I will show you more in detail what the event system is. So this is it. Basically, what happens is that the microservices will produce events. And event is a definition that we gave to it. But of course, you can understand that events, in this case, means like something that's going on in the UI. So a specific action that the user is taking, or something that arises from an API call. And so that helps us identifying like specific moments, specific actions that we want to track. And the microservices, so each one of them has this capability, will publish the events to the broker, which is RabbitMQ in this case. And then we have a whole bunch of event workers that you see on the right side of this diagram that are able to subscribe to the events they are interested in, and then they are able to process them. So why this reaches our goals? Well, first of all, this is scalable because like each single small component is able to implement one single functionality. So if we need, like if we have a peak, for example, of notifications, we can have just more replicas of the notification worker. If we have like a peak of email processing, we can have more replicas of that. So this is very easy to scale at will and according to the actual workload without affecting the other workers. And it is easy to maintain because, and also easy to develop, of course, because each one of them has a very simple functionality attached to it. So when we have to onboard the new engineers, or when we have to come up with something new to add to this system, we can just isolate this functionality, put it in its own small service, and then attach it to the broker, basically. And it can start right away. Of course, this means that all of these components will process more or less the same events, but it's also very easy to add new events in case we need to do so. Later, if we have some time, I will also show you some of the actual client code that we use to publish events, which is very simple. And also, something that we specifically designed to give the system even more flexibility is a distinction between two types of objects in this case, which are the events and the tasks. I will go in more detail about how we define those, but basically for now it will suffice to say that the events are internal-facing actions, something that the application internally cares about. And this, of course, the primary example is the in-app notifications. So you want to show something inside your own app. And the tasks are something that is connected or is related to the outside. So in this case, for example, emails or webhooks and or tracking systems, whatever. So this also helps us define a very streamlined schema. In this case, since we are already on microservices, we use the protobuffers. And so it's very easy to add things and change things inside this schema. Also, thanks to the compatibility guarantees that Protobuf makes. So basically what we do is that every microservice builds a payload, which is like the Go, it is generated, it's the Go code generated using proto-buffers, the proto-compiler. And it puts inside this payload all the information that we might need in this event, and then it posts it to the RabbitMQ. And then there we have in this case, we have 4 event workers, which are going to read these events and do whatever they need to do with that. The central one that you see here is the task converter. This one is a separated component which has 2 main functions. The first one is, well, actually only one, but it has 2 applications in this case. So the first one is to read events, and the second one is to produce tasks from these events. So in this way, we achieve a very clear separation of concerns between all the parts, all the single parts of this system. And then, as you can see, each one can publish their own tasks to the external world or write to the database for the gRPCs to read. So I'll talk about some of the design choices. And the first one is exactly the difference between the events and tasks. I'll go in a little bit more detail. So as you can see, these are the proto-buffer definitions of one of the events and one of the tasks. So as I said, the event is triggered by user interaction most of the time. Not always, because we wanted to keep like some flexibility, but 99% of the time it is triggered by user interactions. For example, you click on something, you create a new folder, you change, like in this case, this is the diagram owner changed the event. So one of the objects that we work with is diagrams, right? So a diagram can have an owner. When you change this owner to someone else, we will generate an event. And we wanted these to be slim objects in this case. So as you can see, the event contains only IDs, basically. And why is that? Because since this is an internal-facing construct, we do not want to put too much information inside this one, because we don't know what the potential nth event worker is going to do with that. So we leave this responsibility to every event worker to do what they need to do with the actual event payload. So for example, in the case of, I don't know, loggers or stuff that publishes to ECR or whatever it is, we care actually about only the IDs, which is the minimal amount of information that you can have in there. And for example, the notification worker might want to resolve these IDs into the actual objects and publish, like, write to the databases some more information about that. So all of them are able to do what they want. The task, conversely, is a fed object because it already has to have all the details in order to do something. For example, in case of emails, you might want to have like the name of the customer, the email address, or all of that. So in this case, we publish the entire package, the entire payload here, so that they can easily fetch the information. They can easily have all the information they need. Also, this way we can simplify a little bit our architecture, because as I showed you here, there is this arrow here which goes from the event system to the microservices, because that represents the resolving action. So the action of resolving an ID into like an actual object. So in case of the event workers, we wanted to give them this opportunity and to query the gRPCs themselves to get the objects they need. And in case of the task workers that you see with the blue arrow here, we don't need this. So for example, our SREs or our DevOps people need to be concerned with less stuff, because they don't have to care about how this is going to connect with those and so on. So it slightly simplifies the architecture. And now the big question, so why RabbitMQ? So we actually considered a few different queue servers and messaging servers, if you want to call them that. And so this is not going to be a comparison between different messaging servers. I'm not going to say that RabbitMQ is better or worse than Kafka or something else. I'm just going to give you some insights into why we decided specifically to use RabbitMQ, and then you can apply, of course, these insights to your own use cases. So first of all, because it supports AMQP. Not only that, but it supports primarily AMQP, which is a binary protocol, which is very powerful. And we felt that it gave us the flexibility that we needed to control basically all the life cycle of the internals inside the RabbitMQ, and a strong standard, which is widely recognized, to work with. The second one is actually, I think, probably the biggest reason. So the smart broker dumb consumer model. We can say that this is actually opposed to Kafka, which is the inverse. This means that smart broker dumb consumer model means that the responsibility of keeping track of what's going on with these messages lies on the server side. So this means that the clients do not need to be concerned with stuff like, do I still have messages to consume in this queue? Or did some message fail to be delivered to me? Do I need to request it again? Stuff like that. So the clients do not need to think about that. And it all comes with the server. And this is very useful because when we want to develop a new microcomponent in this architecture, we can do it very easily. Just by basically, we can just copy-paste the main function from one of the others and add some business logic to it, and that's it. So this is very convenient for speed of development. And then, of course, it supports both PubSub and RPC. This is more of a legacy concern because the monolith that I was talking about, we weren't able to completely get rid of that. There are still some functions that require that because they are like abysmally complex, and I tried myself to fix them, but so far I was not able to do it because I would need to basically redo the database schema. So we just stick to that. And so RPC, the difference between PubSub and RPC in this case is that PubSub, of course, is asynchronous, right? And RPC is synchronous. So basically, we delegated some of the, like the execution of some of these complex functions to the still living monolith app with RPC so that we can keep like at least the synchronicity between the requests. And of course, the PubSub is because in this case is what we wanted for our event system. Then RabbitMQ allows to have arbitrary routing rules. This is also very interesting. I will go into a little bit more detail about the AMQP protocol so you can see how this is relevant. But basically, we wanted to be able to bind queues to publishers in a smart way, like in a way that we found was easy to understand and to maintain, and also with flexibility in mind. And then the built-in monitoring. Again, I'm not saying that other messaging servers do not have those. Maybe they do have. But in our case, we felt that the GUI, the monitoring GUI of RabbitMQ, which ships with it, was like good enough for our needs and required minimal setup. So we just, for these reasons, basically, we decided to go with it. And so, yeah, about the AMQP, so very briefly, for those of you who are not familiar with it, this is a very simple representation of how a AMQP system works. So on the far left side, you have the publisher, which is the component that produces messages. And it sends these messages over to the MQ instance over TCP. As I said, AMQP is a binary protocol. And then the first thing that we have here is the exchange that you see in green. So AMQP defines these two main objects that are key in understanding how it works and in utilizing all the potentiality that the RabbitMQ has to offer. So the exchange is basically an entry point and which dispatches the messages that you send to it to the queues and to the subscribers. So in this case, you have, with the AMQP protocol, you have 4 types of exchange: direct, which is basically going to just deliver your message to the queues connected to it. And if you have 2 queues, it will deliver the message to all of it, matching the routing key. We'll get to it. Then you have the fan out, which just sends the, like a broadcast, it just sends the message over to whoever is connected to it. The topic is basically the same as the direct exchange, but it allows you to use wildcards in the routing key. And so we'll see how this is relevant. So for example, in the case of our email processor, the routing key that we use is email.wildcard, and this way we can get all the messages that are related to emails. And then the header exchange, which is somehow like less used, but it's still very powerful, and which basically allows you to route based on headers like annotations or metadata that you have attached to your message. And then you have the queues, actually, and the queues are normally bound one-to-one to the consumer. So each consumer will have to create a queue for itself to consume the messages coming from the exchange, right? And this is done with the routing key. So the routing key is basically nothing else than a string that, that tells the exchange what messages you're interested in. So for example, you have like foo.bar.baz, and then all messages that are routed with that key will go to that queue. So you know what you're getting, basically. And the queue itself has some powerful mechanisms to control the life cycle of it. So the three most used are durable, auto-delete, and exclusive. Durable means that if the server crashes or you just restart it, it will, like when you start it up again, the queue will be there. So you don't have to redeclare it. And the SRE people don't have to get mad at you because like the queue is not there and your consumers are not consuming, so it will stay there. The auto-delete is basically an option that allows you to tell the MQ, okay, so when I have no more consumers for this queue, please delete it. So if you have like a short-lived consumers or one-off applications or whatever it is, you can just declare the queue auto-delete, and then when you close, when you stop the consumer, the queue will go away. So you don't have to maintain it, you don't have to be concerned with it. And exclusive is, it means basically that the queue can be consumed only by consumers on the same channel. And so that limits basically the accesses that you can have on that queue. This is relevant for RPC, for example. We'll see how. So then what did we do? So after this, we developed a simple Go library, which allows us to abstract some of the complexity that is behind the AMQP protocol. And as you can see on the right side, we have, like, this is a very simple schema of what our library looks like. So at the very base, like, we have the AMQP open source client, which is the Stradway AMQP. You can find it at GitHub. It's very good software. And however, they explicitly stated that they are not going to support some of the functionality because, of course, they're probably very application dependent. So one of those is the reconnect and fail. So our library is, we need that also to make up for these like missing features. Well, so the reconnect and fail is one of those. So what happens if the connection with the RabbitMQ drops? So you have to do something about it. So our library provides that. And then you have some user abstractions to simplify the way that you are declaring objects inside the MQ and the way you are interacting with it in the first place. So if you have a new developer which is onboarded yesterday and you want them to start writing code, you can just give them this and they can use the interface in this library to just run declare consumer, and that's it, and they can start right away. And they can like get up to speed with their time. And of course, some of the goals that we had developing this are also it has to be configurable for advanced use cases. So should we need something more powerful and more control over what we do with the connections, with the queues, whatever, so we have also the lower level interfaces. And we wanted it to be unit testable because because of the fact that we added features, so we wanted them to be testable. And most of the interfaces, like programmer library interfaces that you get from the Stradway AMQP are structs. And so we wanted to provide some more interfaces to make this testable and to not have to rely on an external dependency in our CI, basically. We wanted to be able to run the CI whenever. And so this is what the library structure looks like. So we have like a few packages. The channel package is basically just a wrapper around the AMQP channel, as I said. So this provides just a means for testing the code. The client is the main abstraction. So this contains the big interface that we provided to the external world to use the library itself. The connection package provides some connection level logic. I didn't mention that there is a distinction in AMQP protocol and in how RabbitMQ is implemented also between the connection and the channel. So basically the connection is the actual TCP connection that you have, and the channels are channels, not Go channels. They're AMQP channels that use the TCP connection to connect to the RabbitMQ. So for example, you can have end consumers using the same connection to connect to different queues in RabbitMQ. They decided to implement it this way because like the opening a TCP connection is more expensive than opening a channel in this case. And so you can have like cheap connections this way with the server without having to recreate the TCP all the time. And and then we have the two packages, consumer and publisher, which we basically implement the big interesting logic about consumers actually. So how to read messages from the MQ and how to publish them, including the RPC package, which, as I said, we needed to keep for legacy reasons. So this is an example of the RCP implementation. I hope that you can sort of see the code, but I will just show you some of the key points. So the implementation of this RPC is actually using the interface that we provide in our own library. So we reuse our own code in this case. And some of the things that I wanted to point you to are the queue_declare method. So we use this to declare a queue in this case. The first parameter that you see, which is an empty string, is the name in this case. And if you have a key now, you can see that we have an empty name here, but we use the queue.name here when we create the consumer. Why is that? Well, this is how RabbitMQ suggests to implement RPC, which is something that they did for a C. So basically what we're doing here, we are declaring an anonymous queue, and which will be bound to the default exchange inside RabbitMQ, which every instance must have. And then we use that name, which is assigned by default by the server, to bind the consumer. So basically we're saying we declare a one-time queue, and we attach a consumer to it. And this is just how they recommend to do that. And then we use the option pattern to pass some of the options that we want to use inside the queue declaration. So this is a variadic argument, of course. So for example, in this case, we declare that the queue is not durable. So when the server restarts, it goes away. It is auto-delete when the consumer stops, it goes away, and exclusive true. So these are the options that you want for an RPC implementation. And auto-ACK, of course, so on the consumer. And then basically what you're saying is that you're attaching to the payload some metadata like the correlation ID, which is a unique ID that you need to make sure that the RPC response is the one you're looking for, and the reply to, which tells the consumer, like the RPC implementer on the other side of the RabbitMQ, to know where to respond. And this is how we implemented that. As an additional bonus, we accept the context, of course, in the remote call signature, so that we can make sure that we don't stay there waiting for the response longer than the context that you give us intended to. So here we have a select over the messages, and with the subcontext done in this case. We use the soup context in this case because there is a small gotcha, which is if they pass a context like a background or something with no deadline, then you're going to wait forever anyway. So we need to make sure that we give it a definite timeout in case they don't provide it. And yeah, so I'll go ahead and show you some of the development tips. I have 4 of you. And how to maybe not screw up. Oftentimes it's not enough, but maybe it'll give you a good start. So the first one is to separate connections for consumers and publishers. As I said, the AMQP protocol has this distinction between connection and channels, right? So you might be tempted to use the same connection and different channels for consumers and publishers alike in your application. But this is not recommended because basically of TCP back pressure. So TCP back pressure is that mechanism by which if the client application does not consume fast enough, the TCP window advertised approaches 0. And when it is 0, then your publisher will stop sending data to it, right? So why this is relevant? Because RabbitMQ needs to receive an ACK when it pushes some messages to the consumer. So if there is back pressure going on and your consumer is not able to send the ACK, and therefore RabbitMQ will stop sending messages to your consumer because it has not received an ACK. So it doesn't know whether the consumer is alive or not or what's going on. So because of back pressure, it's recommended to separate these two connections. And in our code, we do that like with a couple of singletons, like we have the publisher and the consumer connections. So we can also make sure that nobody can instantiate more than one connection for each one of those. And so your publisher can be as fast as they want, publish tons of messages, and still not affect the consumer performance, which would be affected if they could not send an ACK. Then a suggestion here is to pass a buffer channel to notify close. So notify close is a API provided by Threadway AMQP, and which basically allows you to be notified through a channel when an OS signal or well, of course, one of the OS signals interrupts the connection, or just wants to close the application. So actually, we had a bug in our production system because at the very beginning we were passing an unbuffered channel into notify close. But according to how you actually architect your code, it could be that the AMQP, this Threadway AMQP library tries to publish on that channel before you have the chance to read from it, and that leads to a deadlock. So you need to make sure to pass a buffer channel so you don't have this problem. About the 20 that you see here, this is actually funny, but on the internet you can find plenty of advice about how you actually need to declare a buffer channel with only one. But we wanted to, like, we did that at first, but we found out that it was not enough. So we were not sure, and we didn't want actually, honestly, to dig into the Threadway AMQP code to find out how many color points they have to publish messages on the channel. So we just went with a high number. But of course, this 20 is just a huge number that in most cases you're not going to need. And then another tip that I can give you is to declare objects dynamically close to the point of views. So this means that every time you start up the publisher or a consumer, you have to make sure that the RabbitMQ objects they're going to work with are there. So if you start up a publisher, you need to make sure that the exchange that this publisher is going to publish to is there. If you start up a consumer, you have to make sure that the queues are there so the consumer can actually start doing some work. And so how do you do that? Well, it's convenient because the exchange and queue declare operations in RabbitMQ are idempotent. So this means that if you call the same exchange declare with the same options like 20,000 times, it's like after the first one, it's not going to do anything. it's basically like delete HTTP delete in REST APIs, right? So you should be idempotent. And so therefore, it does not hurt if you call this code, if you run this code every time you start up the application. This is also relevant if your environment is replicated. And because, of course, if you work in a replicated environment, you might have like 2, 3, 10 replicas of your consumers or of your publishers firing off at the same time. So it's not a problem because AMQP will handle the concurrency of that. And all those that come after that one will basically lead to a no-op. So that's fine. And then, and as you can see here, after declaring the queue, we have to bind the queue to the exchange. And we do that, for example, this code comes from the email processor. So we do that with email.hash, which means email.anything. And this is the AMQP wildcard. You might want to know that there are 2 wildcards in AMQP that you can use, which are star symbol and a hash. But those are different from regex or like bash, for example. So the star actually means one word. And so if you have email.star, it will match everything that has email.something and nothing else. And if you want to match any number of words, they must be separated by the dot. You need to use hash. So it will match email.foo.bar, email.foo.bar.baz. So that's a small gotcha. And finally, this is one of the maybe most advanced features that you have in RabbitMQ, which is the PerfectSize. The PerfectSize is an option that allows you to know, to control the amount of messages or bytes that are allowed to stay on the wire before receiving a NAC from the consumer. So RabbitMQ, so let's say that you pass it a 100, RabbitMQ will start sending messages to the consumer up to 100 unless the consumer sends an ACK first. So this means that the consumer does not send ACKs and you do not have the auto ACK option to true, then the RabbitMQ will continue delivering stuff to you up to that point. In a replicated environment, I do recommend to use 1-0 false, because 1 means that the server will send one message to the first available consumer, and then will send the next one to the next available consumer. So basically, you can achieve a round-robin message sending in this way. And the 0 in this case controls the amount of bytes that you can have there. It's not really important in this case because you're just concerned about messages. So we use 1. And false is controls whether this setting, the QoS is an acronym for quantity of service, and is global or not. This is another gotcha in RabbitMQ because the AMQP protocol defines global in slightly a different way. So global in AMQP itself means shared by all channels inside a connection. And whereas in RabbitMQ, the global means shared by all consumers inside a connection, so the scope is reduced. But anyway, if you have a replicated environment, this is one you want to do most of the time. And if you only have one consumer, for example, you can decide to set a slightly higher QoS so that the RabbitMQ sends more messages at once, and maybe you can improve performance on the consumer side. But we do have a replicated environment, so that's what we go with. And I think, yeah, that's all for today. So thank you for your attention. And if you have any questions.
I think there's time for just one question. So if anybody has one. Okay, so thanks again for your talk.